Hi everyone, welcome to today's class. Today we will talk about data wrangling. We will use about 2.5 lectures to talk about this topic. We will start with data wrangling for one table, namely one data frame. And then the next topic will be wrangling two data frames. And lastly, we'll talk about how to tidy data and how to impute missing values. So that's the outline. Okay, so let's start. So data wrangling is just a data manipulation, right? And includes the following components: subset data, sort and group data, transform data, tidy data, which means cleaning data, and merge data sets. And the goal is, of course, to get data ready for further analysis, either data visualization or modeling purpose. And we use this package, Dplyr. So this one presents a grammar of data wrangling, which is designed to provide commonly used data manipulation tools and have fast performance for in-memory operations. And for more information, you can click this link and check the GitHub repo repository, which has the R code and also something else. Okay. All right. So before we start, let's take a look at tables. We have seen tables already. Tables are a special case of data frame. So in our lecture, today's lecture, we will use this data set called presidential. So this one is built in ggplot2. So as long as you load the ggplot2 library, you have access to this data set. So this one is a very small data set with 12 rows and 4 columns. Name, last name of some presidents, and start and end date of their office, and party. It's a very simple data set. If you take a closer look at the data set, you see that it is similar to a data frame, but not exactly the same. So you see it has a line says a table 12 by 4, right? So it's a table with 12 rows and 4 columns. And column names, this is regular. And then after the column name, there is a line which shows you the data type for each column, like character, date, character, etc. So this is a table. And tables are data frames that make working with big data a little easier. Right? So the table package is included in the tidyverse package. The last time I introduced you this package, tidyverse, which has 9 core packages, which is including tables. And let's see, there are 2 main differences in the usage of table versus a classic data frame. First, printing. By default, it only prints the first 10 rows and all the columns that fit on screen. So it really depends on how wide your screen is. If you have a very narrow screen, then it will only print a few columns that can fit into your current screen. And secondly, subsetting. So tables are, in addition to the dollar operator, you can also use double square brackets to subset data. For example, if we want to pull out the name column, we can do this: presidential double square bracket name. Okay? And then you have access to all of the components or elements in this column. Okay? So you see, it's kind of like a list. Kind of like a list. You can treat a table as a list. You can also refer to the column index. For example, double square bracket 1, you get the same result. Of course, you can also use the dollar operator to pull out the name column. What about single square bracket? You can try it. You'll see that it also works. However, the output will be slightly different with using double square brackets. Okay. It's similar to the difference about using single square bracket and double square bracket when you subset a list. Okay. So if you use single square bracket, you will slice the list. Namely, you will get a sublist from the whole list. And then let's take a look at the printing options. So you can change the default print behavior using the print option. For example, the MPG data frame has 11 columns. So by default, if you print it, it's also a table. If you print it, you may not see all of the columns, right? And for columns that cannot be shown in the screen, that it will list the column name and show some features of the column, but will not actually print the column. However, you can change the behavior using the print option. Just change this argument, let width be infinity, then it will print all of the columns. For example, you will see this. Okay, n is the number of rows you want to print. You can also control the default print behavior by setting options. Just call this function options, like table.width equals infinity. Then when you print a table, you will see all of the columns. So this is an option for table functions. And RStudio also has a built-in data viewer to view the complete data set. The view function, capital V. So let me show you. If you use this function, then you can see the data set as a spreadsheet. So first, you need to load the data set, so the library. For example, I will load the tidyverse package, which includes the package that contains the MPG data set. Okay. Then if I type view MPG, run it, you see automatically the entire data set will be shown in this upper left panel. Okay. So it will show all of the columns and all of the rows of the data set. The entire data set will be shown here. So if you want to have a big picture of the entire data set, you can use this function, view, capital V. Pay attention. And then let's move on. You can coerce a data frame to a table using the asTable function. Change the class of it. For example, the built-in dataset iris is a data frame. But you can change it to a table using the asTable function. Just apply the asTable function to iris and save the result in iris underscore TB, and then check the class. So now it's a table data frame, table, and the data frame. And sometimes you want to turn a table back to a data frame. For example, the presidential data set is a table. If you check the class, you see it's a table. And you can use as.data.frame function to change it back to a data frame. Let's save it as presidential underscore df. So then you see it's a data frame. So sometimes it's necessary to convert a data frame to a table or convert a table to a data frame because you want to merge two data frames together. It's better to let them have the exactly same data type. All right, some other good properties of tables. It never changes the type of inputs. So it never converts strings to factors automatically. And it will never create row names. And so some additional good properties. All right, now let's start to talk about data wrangling for one table. So the Dplyr package provides a set of verbs for data manipulation of one data set. So actually they are 5+1 verbs. 5 basic verbs plus 1. The 5 verbs are select, filter, arrange, mutate, summarize. Select is used to select columns, and filter is used to select rows or filter rows based on some conditions. So it's specifically used for conditional selection of rows. And then arrange is used to order the rows according to some variables or some conditions. And then mutate is used to create new variables with existing variables. And lastly, summarize. So this is used to summarize your data. Namely, it will collapse many values to a single summary. Maybe it's a one value or a few values. It really depends on the function you use in this summarize word part. So this one will change the dimension, collapse. And then there is one more verb, which is the group by verb. So this one can be used to change the scope of each function. So usually it is combined with the summarize function so that you can calculate summary statistics for grouped data for each group according to some categorical variable. And all of the verbs work similarly. Let's see. First, the first argument is always a data frame. It will take a data frame. So in terms of position, for all of these 5 verbs, the first argument is always a data frame. And then the subsequent arguments describe what to do with the data frames. It might be a list of variables. It might be a function. It really depends on which function, which verb you are using, but usually you just list them one by one, the arguments. And finally, the result is a new data frame. So this is also very important. The result is always a data frame. Even if you use the summarize function at the end and collapse data to one row or one single value, that value itself is still a data frame. It's in the format of a data frame. So this is very useful and very important. We'll see. So let's start with the first verb, select. It's used to select columns. So let's revisit the presidential data set for columns. Suppose we only want to retrieve names and party affiliations of these presidents. Then we can use the select word. So it works like this. The syntax is like this. Select the data and then list the variables you want to select. Very simple. For example, if we want to select the name and party affiliation of the president, we can just do this, right? Select. And you see the result is also a data frame or a table in this case. If originally it's a table, then the result is a table. Right? And it automatically print out the result. However, the presidential data set, the data frame, is not changed. Pay attention to that. So this is a new data frame, and you can print it out. But if you don't save it, it will be lost after you run this code, after you create And some other things related to the select verb. So it has, if you have a large number of variables, then there are a few handy options to select multiple variables at the same time. So for example, let's load the flights dataset from the NYC Flight 13 package. So this package is also very useful for us. We will use it in the next part when we talk about emerging data sets at NYC Flight 13. So you can install and load the package if you want to follow the lecture slides or run the code by yourself. And this double column means this flight data set is in this package. If you want to refer to a data set that is building a data set or a function that building in a particular package, you can use this to refer to it directly, the object directly, without loading the package. As long as you have installed the package, then you can refer a function, an object in this way. Anyway, we will use the main data set in this package, the flight data set. And so let's load the package and then use the names function to pull out all of the column names so that we can take a look at all of the columns. So it turns out that it has 19 columns. So year, month, day, departure time, scheduled departure time, etc. Like 19 columns. Suppose we want to select all variables from year to arrival time. Right? So from year to arrival time. Right? So in the data frame, they are next to each other. So they are kind of shoulder, how to say, yeah, just next to each other. They are consecutive. Right? In this case, you can use this syntax. Use colon, year colon arrive. So select flights, year colon arrive. Then all of these 7 variables will be selected. Let's see, we save the results in flight 1, and we print the first row of flight 1. Let's see, this is the result. Okay. 1, 2, 3, 4, 5, 6, 7. Yeah, from year to arrival. And you can also deselect a few variables. For example, I want to select all variables except for these 3, year, month, and day. Then we can do this, minus parentheses, year, colon, day. So get rid of year to day. A very convenient option to deselect a few columns. So see, Flights 2 is a wide data set. If I print it without specifying the how many variables I want to print out, you see it will only print some of them, but we actually print all of them. See. Yeah, I print the first row. Okay. And then some other functions that we can use. First, to start with, ABC. So this one will select all of the columns that start with ABC. Right? So you can specify the letters you want. Right? End with is similar. End with XYZ. And a more general one contains IJK. Contains 3 letters, these letters, like capture string. And lastly, if the column names are similar, right? Something like X1, X2, X3 with a common character part and numeric part, it's a consecutive numeric part, then you can use this number range. For example, we want to select all of the variables with variable name and with time, ends with time. Then we can do this. Select flights ends with quote time. Right? Then we save the result in flies time 1. You got this, right? The names of it. So all of the column names end with time, right? You may also use Boolean operators to combine conditions together. So for example, you want to select all of the column names that contain time and or arrival. We use bar or. Then save the result here. You'll see the columns have either time or ARR arrival. Even this one is selected. Carrier is selected. Carrier is the airline. Right? So these are some functions that can help us to select columns with some patterns in the names. And it's good for selecting multiple columns at the same time. So we're done with select. Select is used to select columns. Then let's move on to the second word, filter. So this one is used to select rows, conditionally select rows. So the basic syntax is filter the data set and then some condition corresponding to some variables usually. Suppose we want to select observations, the presidents with Republican affiliation, party affiliation equals a Republican. Then we can do this party equals Republican. Pay attention, we use double equal. Right? So this is a condition. And then this is a result, which includes all of the Republican presidents. Similarly, we can retrieve the presidents served after 2001. Then year of start office is greater than or equal to 2001. So this year function can be used to extract the year information from a date. As you see, start is a date variable. And we can use the year function to pull out the year. Perfect. All right. So now let's talk about the conditions that we can use in the filter function. So first, we need to use comparison operators. So these are the regular ones, greater than or equal to, less than or equal to, not equal to, and equal. So all of these can be used in a logical condition. When you have two or more comparisons, you can use Boolean operators and, or not. Okay? So pay attention, these, we have learned this before, and, or. So these are for combining two vector logical values, two vectors of logical values, and double and double bar are used to connect two single logical values. So now we are combining two vector logical values. And for set comparison, we can use this membership operator. Percent in percent, x percent in percent, which is true if x is an element of the set Y. X can be a vector and Y can also be a vector. So let's see a few examples. So X is a vector with 4 values, 2, 1, 3, 0. And so see X equals 0. This comparison expression will yield 4 logical values. And not X equals 0. So this will return the opposite results. True, 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 false. From false, 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 true to true, 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 false. So negate the result. And then or, same thing. X equals 0 or X equals 1. Then we have false, true, false, false, or true. So all of these are element-wise. The number of elements we get really depends on the length of the vector, the length of x. Similarly, you see the last one. So the last example shows you how the membership operator works in R. So x in C01 or not. X has 4 elements, 2, 1, 3, 0. So it will take each element in X and check if it is in Y or not. So in this case, this is our Y vector, right? So 2 is not in it, so that false. The second element is 1, and 1 is in it, so true, right? And 3 is not in it, false. Last one is 0 is in it, true. So we have a vector of logical values, and the dimension depends on the length of the first object in this expression, x. So it will take each element of x and check if it is in Y or not. So this is different from the membership operator in Python. Attention. In Python, the membership operator only yields one logical value. So it's kind of different. All right, now let's move on to one example. Suppose we want to select the presidents who started the term before 1977 and Democratic presidents. So 2 conditions. And so year of start is less than 1977 and party equals Democratic. So 2 rows. And another example is we want to retrieve presidents whose party is Democratic or who started the term before 1977. So in this case, we use the vectorized OR. That will have more rows. Okay. So as long as one of the conditions is true, then that row will be selected. So either Democratic or before 1977. Okay. So naturally, we might need to combine the filter and the select verbs together. So for example, suppose we want to find which Democratic presidents served since Watergate, and we want to pull out the name of the president only. We don't want to have other information pointed out. So we can do this. We first take the presidential data set and use these 2 conditions to select rows using the filter, and then feed the result in the select verb, and then select name. Now we'll get this result. And remember, all of the verbs in Dplyr, all of the 5 verbs in Dplyr will return a data frame. So this makes it possible because the result of filter is also a data frame, which is good for the select verb. Yeah, treat it as a new data frame. So apparently the filter verb is nested within select. So it definitely, it's okay, it works. However, you can imagine if you have multiple operations, multiple verbs that you want to mix together, for example, 4 or 5, then if you use this nesting style, then you will have very long, wide line of code. And it's very confusing too, easy to make mistake. So that's why there is an operator which is called a pipe operator, which will sort of represent this nested structure using a pipeline. So we have seen this before. It's percent greater than percent. So the order is you start with the data frame, right? And then run the pipeline from top to bottom, right? And at the same time, within each row, it will run from left to right, which makes sense, right? And after each layer, you have a new data frame. And the new data frame will be fed into the next layer, next verb. So let's take a look at the pipe operator. So this is in this package. The pipe operator comes from this package. But if we load the tidyverse package, then the pipe operator will be automatically loaded. It will be available for us. Right. And let's see the basic syntax. It always starts with a data frame. So data pipe fx. So this is equivalent to f data x. So this x is whatever argument you need for x. And the data frame is pulled out first. Right? So essentially, this is f data x. Apply something on x. Right? And for more than one verb, for example, data pipe fx pipe gy. Right? Remember, it will run from top to bottom. Right? So f will be run first, will be executed first. And if you use a nested structure, then naturally fx will be within the structure. So it is the inner layer. And so fx will work first on the data set. And the result of fx will be fed to g. So that's why G is the outer layer in the nested structure, and so on. So take a look at the previous example. If we use a pipe, then we'll do the following. Take presidential, pipe, filter. So use these two conditions to select rows, and then pipe, select the name of the result of the filter. Then we get this. So this is equivalent to the following, the nested line of code. So very convenient. With only two verbs, it's not that obvious. But later on, in the next small session, you see some examples with a lot of verbs together, and then you see it has big advantage. So how to read it? You can read it in this way: take presidential, then filter Democratic presidents whose start year is greater than 1973, then select the variable name. And so read it from top to bottom. And there are some keyboard shortcuts for pipe or the pipe operator. If you use a MacBook, you use Command Shift plus M. If you use Windows system, use Control Shift M. Right? And you can try it in your R console. Right? So, all right, so this is that's it for the first small session about wrangling one table. Any questions so far? All right, now let's move on to the second small session. So we have talked about tables, and then the 5+1 verbs structure. We talked about the first two, and also the pipe operator. So now let's move on to talk about the last four. The third verb is mutate. Mutate is used to add new variables, to create new variables with existing variables. And there is an additional verb, which is rename. So this is not included in the 5 verbs, but it is sometimes useful. You can use it to change the variable name. If you don't want to use a function like transform a variable, you just want to rename a column, then you can use this verb. Yeah. So let's see. So notice that in the presidential data set, we have the start and end date of the president's office, but we don't have a variable that is used to measure the length of each president's term. We can add a new variable to measure that. We can do the following. So first, let's load some packages. Load the Dplyr package and the ggplot2 package, because this one contains the presidential data set. And in addition to those two, I also loaded this package called lubridate. So this one is also built in tidyverse. It is used to deal with time and date data, lubridate. So now let's see how to add a new variable. So take presidential type and call the mutate verb and create a new variable called term length. So this one, I just name it. So you name it by yourself. And then give an expression, which is equal to end minus start divided by d years 1. Okay. So this d years 1 is the time period within 1 year. So consequently, the result will be the number of years for each president. So the term is measured in years. Okay. And this d years function is built in lubridate. That's why we need to load this package. Then let's take a look, save the result in my presidents. And then you see there is an additional column at the end, which is the term length. It's a double, it's a float. And then these are the first 3 observations. Again, by default, the presidential data set will not be changed. Even after you run this pipe, this won't be changed. If you want to save the results, save the new data frame and give it a new name. I call it my presidents. Then let's take a look at the d years function. So this function is just used to give the duration of time in X years. Right? So if you put 1 here, it will give duration of 1 year. If you type it in your R console after you load the lubridate package, you type this in your R console, you will see this. It is the number of seconds per year. Basically, it's just a measure of time, of 1 year of time. And then if you are curious how many days are in 1 year, by default using this function, it's actually 365.25 days. So it actually is not 365. It considers the lunar year. So adjust for that. All right. Change names. My president have these 5 columns. The last column is called term length. We just created a new variable term length using mutate. If you want to change name, you can use the rename function. It also take a data frame, and then you just specify the new name equals old name pair. So it's in this order. New name equals old name. Basically, it's like you assign the old variable to a new variable, somehow like that. So for example, we can take my presidents and pipe and call the rename function, and I give a new name, term dot length equals term underscore length. And then take a look at the first 3 rows. Yeah, by the way, you can call the head function in the pipe too to show a few rows. So see the last column has been changed. The column name has been changed. However, if you check the names of my presidents, it actually didn't change. Again, so only in the printout, it has been changed. But actually it isn't, it hasn't been changed. So if you want to save the result, give a new name to it, and then check the name has been changed. This is a rename function. This is an additional verb. If you only want to change the column name without doing anything else, you can just use this function. You don't have to use the mutate function. You can also use the mutate function. It will still work, but it's not necessary. And then let's take a look at some functions that can be used in the mutate function to create new variables. So these functions are called creation functions because they will create a new vector with the same length of the original vector or vectors. So you see, take a vector of values as input and return a vector with the same number of values as output. So notice that the mutate function will add new columns, right? So you need to make sure that the new column has the same length with the original vector or vectors. You cannot change the dimension. So functions that can be used to create variables are functions that will do calculation or execution element-wise. So all of the arithmetic operators work in that way, element-wise, plus, minus, multiplication, division, exponentiation. All of these will do everything element-wise, so no problem. And also the log functions, natural log, log base 2, log base 10. So namely, let's see some examples. So y is a vector of 3 elements, right? If you take log 2 of y, you have a vector of 3 elements. So it will not change the length. This is good. You can use it to create a new column. Similarly, exponential functions. So this will calculate e to the x. It will also keep the length. So you see sequence from 0 to 1, the jump is 0.3. So 4 numbers, 0, 0.3, 0.6, 0.9. So this is the entire vector. And then you take you calculate e to these numbers, right? Then you have 4 numbers too. E to the 0 is 1. So anyway, the length won't be changed. And some special operators, modular arithmetic operators. First is integer division, percent divide percent. Integer division is also called floor division. It will calculate the quotient and run it down to an integer. So for example, also the second operator is the modulus, right, or remainder. So this will yield the remainder of the division. Suppose we want to decompose the arrival delay into 2 parts, the number of hours and the number of minutes. Right? So originally it is just the number of minutes, right? The unit is minutes. Suppose we want to separate it to 2 parts. Right? We can do this. So take the flights data set, select arrival delay, and filter out positive arrival delays only. Right? Some flights arrive earlier, actually, so we filter out those. We just consider positive arrival delays. Right? Then use the mutate function to add 2 variables. The first variable is arrival delay in hours. Right? So we use floor division. Arrival delay modulus divide 60. So this will calculate the integer. Right? The integer is the number of hours and run it down to an integer. So for example, if the arrival delay is 30, right, then 30 divided by 60 is 0.5. You run it down to 0. So 0 hours. And the leftover, the remainder, which is 30, will be the number of minutes, right? So which makes sense. And the arrival delay in minutes will be the remainder. So we use this modulus division, arrival delay modulus 60, which is the remainder. Right? And save the result in a new data frame called delay. Right? And then I just want to show you some observations with arrival delay that is greater than 15 minutes. And show the first 5 rows. You see this. Check the result. For example, 51, right? 0 hour, 51 minutes, right? And for greater than 60, 123, 2 hours, 2 minutes. So this example just shows you these two special operators, integer division or floor division and remainder. And all of these are good in creating new variables using the mutate function. Right? If you change the dimension, if you use a function that will change the dimension, for example, you use the min function in it, you will get an error because you change the length of the vector. And there are some cumulative and rolling aggregates. So these are not aggregation functions because it will not change the length. For example, z is a vector 1, 2, 3, 4, 5. The cumulative sum function will be this 1, and then 1 plus 2, 3, and then 1 plus 2 plus 3, 6. So it gradually adds one number to the sum, the current sum, the cumulative sum. And similarly, we have cumulative mean, cumulative product, minimum, and maximum. Right? So as long as the function is cumulative, it will not change the dimension. So they can be used in the mutate function, no problem. All right. And we're done with mutate and rename. Mutate is used to add new variables using existing variables. So basically, it is used for data transformation. And next verb is arrange. So this function is used to sort your data frame according to a variable or some variables. So pay attention, the sort function will sort a vector only, but not a data frame. So the sort function will sort a vector alphabetically or numerically, it's fine, but it cannot be used to sort a data frame. So to sort a data frame, we can use arrange. For example, suppose we want to sort the presidential data by term length from the longest to the shortest. We can do this. Take my presidents. So this is a data frame we created with the fifth column, which is term length. Okay. Arrange it according to term length, but in descending order. So if you want to do it in descending order, you have to add this DESC. Then this is the result. Okay. And by default, it's in ascending order, of course, from smallest to largest. All right. And again, the range function will not change the original data frame. So if you type my president again, it's not sorted. If you want to save the result, save it, give a name, save it. And then this my president one is sorted. You can also sort the result by multiple variables. For example, I want to arrange the results, the data in descending order of term length and start time, because otherwise there will be ties, right? There will be ties in it a lot. Many people have served 8 years or 4 years. So you have the option to add more variables in arrange. So this is a result. It's a range. And the last one is summarize. The last function in the 5 verbs is summarize. There are 2 versions, summarize Z or summarize is S. It doesn't matter. I think they are equivalent. Originally, it was summarize with S in it. So let's see how to use this verb. So this one collapses a data frame into a single row. How many values in a row? It depends. Depends on the function or the number of variables you created in the summarized part. So we have to specify how we want to reduce an entire column of data into a single value. For example, take my presidents, my type, summarize. We can calculate a bunch of variables. N is equal to n parentheses. So this function, n parentheses, calculates the number of rows in each group of data. Because we haven't called the group by variable yet, so it will just simply calculate the number of observations in your data set, in the presidential data set, my presidential data set. So no argument is required, but you need parentheses. So this will calculate the number of rows. And then first year is a new variable, which is the minimum of the start date, year of start date. And last year is the maximum of the end date, year of end date of all of the presidents. And then number of Democratic presidents. So that will be sum of party equals Democratic. So this one will yield a vector of logical values, true or false, and the sum of them is the number of trues, so Democrats. And then total of years, which is the total term length, and then average term length. So if you take a close look at this chunk of code, you'll see that each variable will take a column or the entire data set and collapse it to one single value. Each of them, totally 6 of them. So we will create a very small data frame or a table with 6 columns and 1 row because each one will only yield 1 value. So this is the result. N is 12, first year, last year, a number of Democratic presidents, total term, and average term. Okay. So this is how the summarize verb works. Right? It will take a vector and yield 1 value. And many times the summarize verb is combined with the group by verb to change the scope. For example, in the last slide, we calculate that the average term length for all of the presidents is 5.67. Then you may be curious about comparing the average term length between the 2 parties. Which party has longer average term length? In that case, we can group the data by party first. So take my presidents group by party and then calculate some summary statistics. For example, we can still calculate the number of presidents and then average term length. At the same time, we can calculate the standard deviation of term length and then save the result. So now we have grouped summary of data. In particular, you can compare their average term length. Turns out that Republican has slightly higher average term length compared to Democratic, but very close actually. Right? And the standard deviations are also very close, 2.32 versus 2.34, and number of presidents. So that's why the group by this verb will change the scope of calculation. Basically, it will group the data first and then calculate something for each group. So party only has 2 unique values. That's why in the summary table, in the result, we have 2 rows. If there are like C categories in the grouping variable, then you will have C rows in the result. It really depends on how many categories. You can also group the data by 2 or more categorical variables. Then the number of rows in the summary table depends on the number of unique combinations of the values in the 2 or more categorical grouping variables. It really depends on. All right. And similar to mutate functions, there are some functions that we can use in the summarize word only. So only those aggregation functions can be used in the summarize function because you have to take a vector or vectors and collapse them to a single value. Otherwise, you cannot use them in the summarize. So first, the median function, quantile function, minimum, max. So all of these will take a vector and yield one single value. Quantile function, pay attention, it by default will yield 5 numbers if the 5 number summary. But if you specify which percentile you want to calculate, then it will yield one value. And also some functions related to counts. So this n parenthesis, we have seen this before, will yield the size of the current group. See, the current group, 5 and 7, will count number of rows. And n distinct x counts the number of distinct values of a variable x. So this will also take a vector and yield one single integer, which is the number of distinct values. And this one will also will count number of non-missing values. So this not is done NA will yield a vector of true or false values. So if it's missing, then false. If it's not missing, true. And then cover the sum, that will be the number of non-missing values. So, and the second, this part is counts and proportions of logical values. So I have mentioned this before. Right? In R, true is equivalent to 1 and false is equivalent to 0. Right? Somehow like this. If you have to do some calculation using true or false values, they will be treated as 1 and 0s. Right? So for example, you compare x with 5, then you have 4 true values and 6 false values, right? And then we can actually cover the sum of them and also the mean of them. The sum of a logical vector is the number of true values, And the mean of a logical vector is the proportion of true values. Proportion of true. So we can use it to summarize logical vectors or to check some conditions. What percent of observations satisfy a certain condition, etc. Right, so we can use this property. All right. And then let's move on to the next small topic, handling missing values. So in this lecture, we will just talk about the simplest rescue, which is deleting those observations or ignoring those values. And in the last lecture, we'll talk about how to impute missing values using some packages. So in R, missing values are denoted by NA, not available, which represent an unknown value. And almost any operation involving an unknown value will also be unknown. So NA will produce NA. So missing values are contagious in R. So for example, x is a vector of 5 values and the third one is missing. Then if you add 10 to x, then the missing value will yield the missing value because R doesn't know how to handle it. It can only yield the missing value. Okay. So for this kind of math arithmetic operators, it does everything element wise. It doesn't matter that much because it will just yield one missing value. But what really causes problem is using its aggregation functions because usually it will just yield a missing value because it doesn't know how to take average of missing value and some numbers. So to avoid this problem, as we have learned before, we can add this argument na.rm equals true to ignore missing values in the calculation. Then we have a valid value. And the summary function is special, right? Summary function will automatically ignore missing values, and also it will calculate the number of missing values for you. So this is kind of a special case, right? And to filter out all observations in a data frame with missing values in a variable x, you can use this kind of syntax or code. Right? So take the data, filter, right? Not missing x. X is a particular column in it. So this will remove all of the observations in missing values with missing values in x. Okay. So alternatively, we can use the drop NA function in tidyr. So the pandas package in Python also has this function drop NA, exactly the same function. Okay. So you can take data and pipe drop NAX. So this will remove all of the observations with missing values in x. Right? So same thing. Just pay attention. These two functions is.na as not is.na and the drop na only works for real missing values. Right? That values that are actually denoted by NA. If the missing value are coded in some other ways, then they won't work. Right? Just pay attention to that. And then let's take a look at some examples. So we first create a very small table. So notice that I load the tidyr package and create a table. And so table can be created in this way. You just specify the two columns, the columns you want. Okay. The 1, 2 missing, A missing B. So this missing value is denoted by like triangle parentheses NA because this is a missing value, missing character value. Okay, so this is a missing double value, but essentially they are all missing. Right? You can use drop NA or is NA to remove them for sure. So let's see if we want to remove all of the observations with any missing values in any column, then you can just take the data frame and pipe drop NA without anything. Then you see the result. Only the first row is left because the second and third row both have missing values, right? If you only want to remove missing values in one variable, then specify the variable name in drop NA. For example, I only want to remove observations with missing values in x. Then we do this. Then we see the second row is retained because it still has a valid value to the x column. So this is also very useful because the situation of different column may be different. And maybe X has a few missing values only, so it's okay to remove those rows. But Y probably has a lot of missing values. Then it's not ideal to remove all of the rows. You will waste a lot of data. In that case, we probably choose to impute missing values in Y. So different strategy, but different columns. All right, great. Then let's see a few extended examples in using the 5+1 verbs in Dplyr to answer some data exploration questions. For example, let's use a flights data set again. So, by the way, this package has information of all flights departed from NYC in 2013. So it is quite a big data set, contains all of the flights departed from New York City in a year in 2013. So that's why it's called NYC Flights 13. It actually has 5 data sets, and the flights data set is the main data frame, main data set. Suppose we would like to know which carrier has the longest average departure delay on January 1st, 2013. So to answer this question, we will just use the verbs that we have learned. Right? Just examine the question first. Let's take a look at the columns that we need to use to answer this question. So first, carrier, which is the airline. This column is required, right? And the departure delay, right? So departure delay is required. And also the month, day, and year. So all of these are required. And yeah. So basically we need 5 columns. So that's why we first select these 5 columns. Okay? And the rest of them are not necessary. So ignore them. So take flight, type, select this. And then we will filter because we only care about flights on January 1st, right, the first day of 2013. So we will use this filter to filter the related flights, month and day. Right? And also suppose we want to consider positive departure delays only. Right? So then we add one more condition. Departure delay is greater than 0. We use AND to connect all of these conditions together. And then take a look at the question again. We want to compare average departure delay between carriers or airlines. That means the basic unit in the comparison is airline or carrier. That's why it makes sense to group the data by carrier before we summarize the result, namely calculating the average delay, right? So we first need to group by carrier and then call the summarize function. Create a new variable, which is the average departure delay, which is the mean departure delay. And pay attention, there are missing values in this column, so don't forget to specify this. So after this row, we will have a small table with on each row of which is corresponding to one airline, right? And arrival delay. And lastly, we want to know which one has the longest. So which means we should sort the result in descending order of departure delay, average departure delay. So that's why we do this last. And save the result in delay. This is the result. So this is how we answer a question using Dplyr verbs. So see, we do everything in a very precise way. We didn't waste anything. We didn't select any variables that are not necessary. So this is one example. And a second example is For example, which destinations have the longest average arrival delay on December 25th, 2013? So following the same strategy, we first select the related variables. We apparently need destination. For all of the flights, the departure, so there are three airports in New York City, but the destinations are very different. Right? So we need to select the ST, right? And arrival delay, apparently, and also month, day, and year. All of these are required. And filter the flights on this day, Christmas Day, and also allow delays. And now we're comparing average arrival delay among destinations. So that's why we need to group the data by ST, now destination. And then calculate average arrival delay, arrange result in descending order of average arrival delay. Get the result. So it turns out as this. And you can see that the destination airport are denoted by their airport code. So kind of difficult to understand for some of them. So in the next lecture, we'll talk about how to add metadata to a main data frame so that we can have more understanding of data. And the last one is which carrier has the highest average speed to San Francisco? So this one involves creating new variables because in the data set, there is no speed, no variable that is used to measure the speed. We need to calculate it by ourselves. So first we select variables. We need airtime, distance, destination, and carrier. Because distance divided by airtime. Airtime is the time in air. Okay, distance divided by time is the speed. Right? And destination should be San Francisco only. Right? And carrier is related because we are comparing among carriers. And then filter out flights with destination equals San Francisco. And then we calculate a new variable, which is the speed. So when we calculate a new variable, we need the mutate word. So speed equals distance divided by airtime times 60. That's because airtime is measured in minutes. So distance divided by airtime will be the speed in minutes. But usually we measure the speed in hour, so per hour. So multiply it by 60, that will be distance per hour. Okay. And then more missing values, and then group by carrier. So and calculate average speed, and then arrange by average speed in descending order. So UA is the fastest, okay, 450 miles per hour. And then Delta and some other airlines. From this example, you see that although it seems very straightforward, it's still very important to order these verbs. Right? You see select filter usually, and if you want to create any new variable, you need to do it before group by, actually. Right? But group by should always be before summarize. Because you want to calculate some summary statistic for each group. So group by is always above summarize. Right? And then arrange usually is the last word because you want to sort the final result according to some order so that you the result that is of interest will be on the top of your output. Hello, everyone. Today we will continue to talk about data wrangling. So in today's lecture, we will talk about how to merge two data sets, two data frames. And also, if we have time, we will talk about how to tidy data using the tidyr package. Okay. All right, let's start. Where are we? Last time we finished the topic about wrangling one table, talk about the 5 verbs plus one group by, right, and also the pipe operator. So today we'll talk about wrangling 2 tables. So data analysis usually involves managing multiple tables, multiple data sets. That is because these tables are called relational tables because it is the relations, not just the individual data sets that are important. Okay, so relations are also very important. And we will continue to use the Dplyr package. And in this package, there are 3 families of verbs that work with 2 tables. So it's 3 groups of functions that can be used to deal with 2 tables. The first group is called mutating joins. And the second one is filtering joins. And the last one is set operations. So mutating joins are used to add new variables to an existing table. So it's kind of like the verb mutate when we used to deal with one table. So that's why it's called mutating join. And the second group, filtering joins. So these are used to filter observations from one table based on whether or not they match an observation in the other table. So filtering joins are used to filter rows or selecting rows. Mutating joins are used to select columns or add columns, add new variables. And last one, set operations. So the functions in this group are similar to those functions we talked earlier in base R. There are some functions that can be used to deal with sets, for example, union, intersection, and set difference, etc. So there are some parallel functions in Dplyr that can be used to combine observations in different data sets as if they are set elements. Right? So basically treat each data set as a set, right? And each observation, each row is one element in a set. So that is the third group, the set elements. So this discussion assumes that we have tidy data, which means all the data sets are clean, and each row is corresponding to one observation, and each column is corresponding to one feature or one variable. All right, so we start with mutating joins. So this join is the most important and most commonly used join family in Dplyr. So it first match observations by their keys, key variables, and then copy across variables from one table to the other. So they can be used to add new variables to an existing table, just like the mutating function. All right. There are 4 types of mutating joins: inner join, left join, right join, and full join. We start from the inner join. So we first create 2 toy data frames, toy tables, because using these kind of simple data sets is very clear. Okay, so to make the operations very easy to understand. So the first data set or table is called X, and it has 3 rows and 2 columns, right? A key column, and the value column, value X. So the key column contains double values, 1, 2, and 3, kind of like ID. And the second table is called Y. And it also has two columns, a key column and a value Y column, right, which is also a character. And the 3 rows. Right? Notice that the key values are not exactly the same. Y has 1, 2, 4, and X has 1, 2, 3. Now let's start with inner join. Right? The basic syntax is inner join X, comma, Y. X is called the left table, Y is called the right table. And then let's do it. Let's use the pipe operator, right? X pipe inner join Y. So this is essentially the same with inner join X, Y. Okay. But we just use the pipe syntax. And immediately you see this message is printed. Okay? Joining with by equals join by key. And this key variable is figured out by the function. It will automatically find the common variable in the two data frames. Apparently, in our example, the common variable is the key variable. They have exactly the same column name. So key is used as the key variable that is used for matching, kind of matching purpose. And then this is the result. So see, only the rows with the matching key value are kept in the result. So you see, both of these X and Y data sets have key values 1 and 2. However, the third row, right, the third observation don't have the same key values. So the third row of X and the third row of Y are removed from the result. Only the first two are kept. So this is the most important feature of inner join. Right? So any unmatched rows are not included in the result. So of course, by doing so, we will lose some information. We will lose some observations for sure. So this is an inner join. So that's why inner join is not preferred usually because it will lose information. Instead, the most commonly used mutating join is left join. The syntax is left join X, Y. X is the left table. Y is the right table as usual. And if we use a left join, then all of the rows in the left table, namely the X table, will be kept, will be retained in the result. And only rows that have a matching key value in the Y table will be kept. And also variables in Y will be added to X. So let's do a left join for X and Y. X left join Y, join by key as usual because key is the common variable. And then this is the result. So see the entire X table is kept, but only the first two rows of Y, Y values will be added. And a missing value is automatically filled for the Y, for the cell when the Y column does not have a value because the Y table does not have key value equals 3. And so a missing value is automatically filled. So this is called a left join, it is good for joining some metadata with some main table. So of course, in this case, the left table is the main table, and Y is used to add some supplementary data, some new variables. This is the left join. The left table will kept complete. And the right join will do a similar job, except that the right table will be complete, will be kept intact in the result. For example, if we do a right join for X and Y, you see all of the values in value Y will be kept. So the entire Y table is kept in the result. However, the X values, the left table, only rows with matching key values will be kept in the result. And missing value will be filled. So this is a right join. Very similar to left join, just except that the right table will be kept complete. And however, you see, because X is the left table, Y is the right table, still variables in Y will be added to the right of the resulting table. Okay, so the order of the variables will stay the same, will be the same, even if you do a right join. Okay? Value Y will be the last column because it is from the Y table to the right table, and it is added later. Okay, we start with the X table. And last one is full join. Full join will include all observations from the two tables, no matter there is a matching key value or not. So let's do a full join. So you see, this is the result. Both the left table and the right table are complete. And missing values are filled if necessary. This is a full join. So if you don't want to lose any information after the join action, then use a full join. So this is the most generous case. And the left, right, and full join together are called outer join. So compare with the inner join. The inner join is by itself. Is by itself. It will delete. So potentially both two tables won't be complete after the join. But the left join, right join, full join will keep at least one table complete. So this is mutating joins. And sometimes, so ideally the key variable, the variable that we use to do the matching job, should contain distinct values, okay, no duplicate keys. However, in practice, it's possible. For example, let's create two new tables, X and Y. So you see, X has two rows of with key equals 1, and Y also has two rows with key equals 1. So duplicate keys, this means. Then if we do a join, for example, a left join, X left join Y, then you see we have a warning message putting out. Detected an unexpected many-to-many relationship between X and Y. Okay? So that means many-to-many. Okay? Then the join doesn't know how to do the matching anymore. Okay? Should it be 1 to 1, 2 to 2, or 1 to 2, 2 to 1, etc. All of them are possible. So instead, it will do a Cartesian product of all of the combinations. So eventually, we get the result like this. It will match. Consider each combinations. X1 with Y1, X1 with Y2, X2 with Y1, X2 with Y2. All of the possible cases. So 2 rows times 2 rows, totally 4 combinations. So this is the case when we have duplicate keys. It will create Cartesian products of the matching observations. So now let's take a look at the NYC Flight 13 package. So as I said last time, this package contains information about flight data that departed from New York City in 2013. And there are actually 5 tables in this package, and the flights table is the main table, which contains some the information about each flight. And let's take a look at the data set again, the main data set again. Because this data set is very wide, it has 19 columns. So let's select a few columns and call it flights part and print 3 rows. Departure time, arrival time, carrier, flights, etc. Okay. And if you pay attention to the values, you see in some of the columns, we have some code. For example, the carrier airlines, we have code, and also destination airport, origin airport, and also, so all of these have some kind of code. It's difficult to interpret and understand. So that's why sometimes we need to add some metadata into the main table to better interpret the columns. Okay. And also take a look at the origin. We know that all of the flights were departed from NYC. But there are 3 airports actually, like JFK, LGA, LaGuardia, and EWR, 3 airports. So take a look at the distribution of the 3 origin airports in NYC. So 3 of them. Just pay attention. Although all of them departed from NYC, New York City, they are from different airports. Now let's take a look at the code book or metadata for the flights data set. So there are actually 4 more tables. The first one is called airlines. This one contains the full carrier name and its abbreviated code. So in the flight data set, the airlines or the carrier there are abbreviated code values for the airlines. But this one provides full carrier name, airline names. And airports. So this one gives information about each airport, geographic information, etc. And then planes. So this one gives information about each plane for the specific flight. Specifically, it has a tail number and some other information. For example, manufacturer year. And the weather. So this one gives hourly weather data for each NYC airport. So this weather data set is only about the origin airport, one of the 3 origin airport. All right, let's take a look at them one by one. First, the airlines data set. 2 columns only. First one is a carrier code. For example, probably you are familiar with UA, AA, like Delta. Right? But some of them might not be very familiar, like the first one, 9E. It stands for Endeavor Air Incorporation, etc. And B6 is JetBlue. Right? So this one contains carrier code and their full names. And in this data set, apparently the carrier column is a unique identifier, right? Because each airline has a unique carrier code. So in this case, for this data set, this variable carrier can be used as a key variable. For example, when we do matching, when we do merging or join, we can use this as a key variable to do the matching. And the second metadata data frame is airports. So this one contains a few variables about the airports. Right? They may be the origin airports or the destination airports. Right? So the first column is called FAA. So this is the FAA code for each airport. FAA stands for Federal Aviation Administration. That is a unique code for each airport. And then we have the name latitude, longitude, altitude of each airport, and time zone offset from the GMT time zone, the standard time zone. And DST is daylight saving time zone, either A equals standard or U unknown. Airports in the US should have standard daylight saving time zone, but international airport may not have this. Okay. And lastly, time zone, the exact time zone. So this is not the same with time zone offset. This is the time zone calculus string. So this is airport. So apparently for this data set, FAA can be used as the key variable because it contains unique values. And next one is planes, information about plane. The first column is tail number, and then year of construction, year of manufacture, and then type, manufacturer, etc. Okay. So for this data frame, which variable is appropriate to be used as a key variable? Anybody? Okay. By our standard, the tail number should be used as a key variable, right? Because it contains unique values. All right, let's move on to the next one, okay, weather. So this one is a little bit more tricky. So it contains hourly weather condition for the origin airports. There are 3 origin airports, okay? So it has 15 columns. Origin, year, month, day, hour. So all of these are used to define the hour of each observation. And then temperature, the EWP, humidity, wind direction, etc. A lot of information. And the last one, time hour, is a combination of the date and hour information for each observation. So for this data frame, to create a key variable, we need multiple columns, apparently, right? Any single column cannot be used to define, to uniquely identify one observation. So this time hour is very close. It contains the date and hour of the observation. However, remember, there are 3 airports in New York City. So you have to identify the airport as well. So to create a key variable, we should combine these 5 columns together, origin, year, month, day, and hour, to create a unique key variable for this data set. Alternatively, we can combine time hour and origin together. Okay. However, this variable is not contained in other data sets, other tables. So technically, it is not usable. Okay, we should still use these 5 to create a key variable to do the matching. All right, so this slide shows you the relationship between or among the 5 tables. Flights is the main table, right? And these arrows shows you how they are connected. For example, airport and flights are connected through this FAA code in the airport data set and origin and destination in the flight data set. So in the airports data set, the FAA code is just called FAA because there is only one column that is about airport code. However, in the flight data set, there for each flight, there is an origin airport and the destination airport. we have to differentiate them. So that's why they have different names. But both of them are FAA code, actually. And planes, definitely we should use tail number to match them, to connect them. For weather, as I said, we have to combine all of these 5 variables to create a unique key variable. So consequently, these 2 tables will be connected using these 5 variables. And lastly, airlines, carrier, the airline. So this is a relationship, okay? And then after we see that, let's use some mutating join functions to add metadata information to the flight data set. Because we know that whenever we use a mutating join, the new variables will be added to the right of the existing table, the left table. Consequently, it's difficult to see the result if your left table is too wide. So that's why let's create a narrower table from the flight data set. We select year to day, our origin, destination, tail number, and carrier from the flight data set and call it flights 2. And then suppose we want to add airline names to the flights data set. We can do this. Flights 2, pipe, left join, airlines. And save the result in flights 3. And you see automatically this join was by the carrier variable. So this is a common variable of these 2 data sets, flights and airlines. So this is the result, the first 5 rows. Right? So you see this column is added. Right? This is from the right table, the airlines table. Yeah. This is from airlines table. It's added to the right of the table. And controlling how the tables are matched. So notice that so far when we do a join, mutating join, we didn't specify the key variable that is used to do the matching job, right? So actually Dplyr allows multiple ways to specify the matching variable or the key variable. The first option is null. So by equals null. So that is what we did so far. We didn't specify the variable we want to use to do the matching. In this case, Dplyr will use all variables that appear in both tables with the same column names, of course. All variables. If there are 2 variables, then it will use 2 variables, okay? So, for example, so the weather data set has all of these, okay? And also the flight data set also have these variables. If we do a left join for flights 2 and weather, then automatically the join will be by all of these 5 variables, right? Because they are all existing in both tables. So then the join is done correctly, actually. Okay. However, this might not be always be the right choice. For example, if we want to join flights 2 with planes, the planes table. Remember in the planes data set, there is a tail number and there is also a column called year. However, the year variable in planes is the manufacturer year of manufacture. Is not the flight year. But in the flight data set, year is 2013. It's very specific. It's the flight of the year of the flight. So although they have the same name, they contain different information. In this case, we must specifically specify the by argument. So by equals tail number only. Otherwise, it will use tail number and year at the same time, and we probably will not get anything, okay? And no observation in the result because there won't be any matching tail number and year. So this is the second option. I specifically specify the by argument, which variable we want to use to do the matching. Okay. And notice that after we do the join, the year columns in the output are disambiguated with a suffix. Okay, so namely, it will keep both the year columns in the result, but it will give a suffix. Okay. For year in the left table, it's at year.x. So this is the year from the flights table. Okay. And year.y, so this column is from the planes data set, okay? Year of manufacture. So it won't lose any information. But of course, you can change the names using the rename function to make them more meaningful. I give a new name to them. Okay. All right, so this is the second option. And sometimes the two tables contain the same information. The two tables have two columns, two variables, which contain the same information. However, they have different names in the two tables. In this case, we need to use this kind of syntax to specify the key variables in the two tables. By equals C parentheses V1 equals V2. Use quote. V1 is the key variable in the left table. V2 is the key variable in the right table. Right? So they have different names, but they contain the same information. We use this to do the matching. For example, we know that in the airports, in the flight data set, there are two columns that contains airport information, destination and origin, both of them, okay? So although they all contain FAA code, they have different names. And in the airport data set, the column is just called FAA, so they have different names. Suppose we want to add the airport information, airport name, to the destination airport for each flight in the flight data set. We can do the following. Right? So flight left join airports by equals C, destination equals FAA. So this will add airport names to destination airports. Similarly, if we want to add airport names to the origin airport, we can do this. Let's see the result. So this is corresponding to the first join, left join. So see, for example, Miami information. So this is corresponding to the destination airport. This is the name of the destination airport. And if we add name for the origin airport, so see, for example, this is JFK, right? We match, right? And LaGuardia, we also match, right? So this is a case that the key variables have different names in the two tables. You use this kind of syntax. Oh, this is the last slide of this session. All right, let's move on to continue. We're done with mutating joins. Mutating joins have four types: inner join, left join, right join, full join. And all of them will add new variables to the left table. And now let's move on to the second and third families of joins. The second one is filtering joins. Take a look. So filtering joins match observations in the same way as mutating joins. However, it affects the observations, not the variables. So this is very important. It will change the number of rows, but it will not add new variables. It will not change the number of columns, even after we do a filtering join. There are two types of filtering joins, semi-join and anti-join or anti-join. Semi-join keeps all observations in X that have a match in Y. So X is the main table and it is the focus, right? And we use Y to filter rows of X. So whatever the result is, the rows are from X, right? They are not from Y, and there will be no new variables added from Y, right? And anti-join or anti-join does the opposite. So this one drops all observations in X that have a match in Y. Still, it works on rows in X only. It will not add new variables to X. It will only use Y to filter observations in X. Right? So it does it in the opposite way. It only keeps the unmatching observations. So let's see some examples. So for example, so these semi-joins are useful for matching filtered summary tables back to the original rows. For example, we first find the top 5 most popular destinations in the flights data set. We can use this pipeline to figure it out. Take flights, group by destination, then use a summarize function to calculate the number of observations in each destination airport. Right? Then sort the result in descending order of n. So then the most popular one will be on the top. Okay? The one with the biggest count will be on the top. And then we use the head function to subset the top 5 and save the result in top 5 DESD. So this is just the summary table we get from the flight data set. So these are the 5 most popular destinations. Alternatively, we can use the following code. So instead of using all of these, we can use the count function, right? Count destination. So it will just automatically count the number of observations in each destination. And then sort equals true. So interestingly, by default, it will sort in descending order. And this is the result. Okay. Same result. Right? So this is the summary table. Then we can use it to filter flights that actually went to these top 5 popular destinations. For example, we can do so first, let's just use the filter verb we just learned in last lecture. Right? We can do it too. Right? You can do this using this membership operator. Take flights and then pipe filter destination in top 5 destination. So this destination is from the flight data set, okay? And if the destination is in the destination column of the top 5 popular destination, then select that row. And so then we get the result. So we can quickly check the result. So indeed, only these 5 destinations are selected. Only flights that went to these 5 destinations are selected. Right? And the summary statistics should be the same with the previous table. We can also use a semi-join to do it. Take flights and semi-join top 5 So this is the left table. This is the Y table. In the standard syntax, this is X, this is Y. And then specify the column we use to do the matching job. So by equals DST. And then, so you can forget about this if you only want to select the flights. And then if you want to furthermore check the result, then add another layer of step, right? Add pipe, count, like this. So this is the exact same with this. Okay. So this is how we use semi-join. It is used to use some summary table to filter some observations, filter out some observations. Now anti-join. So this one is used to delete some observations, some rows, according to some standard. It will delete observations with matching values in the Y table. For example, we observe that there are some planes don't have a matching tail number in the planes data set. So this one anti-join is used for diagnosing join mismatches. For example, many flights in flights don't have a matching tail number in the planes table. So which means the planes table is not complete, right? It does not have all of the tail numbers of the flights in the flight data set. So let's try to figure out those flights without tail number. We can do the following. I take flights, then anti-join with planes. Again, this is the X table, this is the Y table, and by tail number, then count tail number, sort equals true. And this is the result. Right? So it turns out that 712, there are 712, actually there are 722 rows, right? So these many flights don't have a matching tail number in the planes table. That's it. Okay. Not that flights, and unique numbers, unique values, and not exactly flights, because each unmatching, mismatched tail number has multiple observations apparently. And the largest category is missing. So many of the flights have missing values in tail number, about 2,500 of them. And then this tail number has these many observations, etc. So anti-join is used to find mismatches in the join. And then we have some toy examples to show the difference and relationship between the two filtering joins. So we first create two tables. Like the first one has two columns, X and Y, and 4 rows. And the second data frame called DF2 has 3 rows and 2 columns, like X and Z. Okay. And now let's first do a semi-join. Take DF1 and then semi-join with DF2 by X. So if we observe these two tables, because these two tables are too simple, it's very easy to eyeball the result. Semi-join, that means only only observations with matching key values will be kept in the result. Right? So only these 2 rows will be kept. Right? So this is the result. So this example shows you exactly how a semi-join does, and also you see this variable z won't be added to the new table, right, to the result. So it will, based on the left table and the result, all of the rows are from the left table only. And the right table, the Y table is only used as a tool to filter observations. And anti-join does the opposite. So we select all of the rows that don't have a matching value in the X column. So in this case, you see 3 and 4 are not contained in the Y table. So these two rows will be selected. Okay. Again, both of them are from X, from the table, from the df1 table, not from the df2 table. And the results are complementary. If you union these two sets, you will get the original df1. All right. Exercise, we'll skip those. All right, let's move on to set operations. So this is the last family. There are three basic functions: intersect, union, and set difference. Notice that they have the same name with the base R functions: intersect, union, and set difference. However, pay attention, these functions are from Dplyr. So they work on data frames. They work on data sets instead of sets. The base R functions are used to deal with sets or like arrays, like vectors. But for these, both this X and Y are data frames. So the intersect function will return only observations in both X and Y. The union function returns unique observations either in either X or Y or both X and Y. And set difference return observation in X but not Y. So in this case, X and Y are two data sets with the same columns. They should contain similar columns. The only difference is they contain different observations, different rows. So let's see some examples. We'll create two toy data sets tables. df1 has two rows and two columns, X and Y. And df2 also has two rows and two columns, right? Same variables, X and Y. Right? Then it makes sense to do set operations, right? Otherwise, it doesn't make sense at all. And notice that the first row, the first rows are the same for the two data sets. Right? The second rows are different. Now let's find this intersection using the intersect function. Naturally, the first row will be in the result. The union will contain observations that are in A, in df1, dfb, or in dfb, or df2, or in both. Right? So totally 3 rows. And we follow the convention, which means there won't be any repeated rows in the result. We'll calculate the union. Only one copy of the overlapping area will be kept in the result. Okay? And set difference. This also works in the same way as the base R function. So again, let's show the two data frames again. So set difference df1, df2 will remove common elements in df1, df2 from df1. So the common elements is the first row, right? First row. So the first row will be removed from df1. So consequently, the second row of df1 will be retained, will be in the result. And if we start with df2, then the common rows will be removed from df2. So consequently, so this row will be left, will be retained in the result. All right. So these are the set operations, set differences. All right. Any questions? You have no questions, let's move on. So next small topics is data import with read-R. So read-R is part of tidyverse. It contains some functions that can be used to efficiently read in data sets, also different types of data. So there are some functions. The read underscore CSV reads comma delimited files, like CSV files. And this one, CSV2, reads semicolon separated files. And TSV reads tab delimited files. So these are the files with separated with tabs. And last one, read underscore delim. So this one can be used to read in any type of files, right? Files with any types of delimiter. So this is the most general one. And so these functions all have similar syntax. We'll focus on read underscore CSV. Let's take a look. Right. So we have a survey.csv file. Right, so this one contains, so if we use this to read in the CSV file and call it survey, automatically some information will be provided. Number of rows, number of columns, and the data types of columns, and some other information. And then if we print out survey, so this is the result. So this is a regular CSV file with column names already included and no, and it starts from the very first row. The very first row contains the column names, so no supplementary information or metadata at the beginning or at the end. Then you can just directly use this code, this type of code without any additional arguments. And so by default, the read underscore CSV reads the first line of the data for column names. And if, for example, there are some description of the data at the beginning of on the top of the spreadsheet or CSV file. For example, there are 3 lines of code, 3 lines of text at the beginning. Then you can choose skip. You can use skip equals n arguments to skip the first few lines. So in our case, we can skip the first 3 rows and then get the correct result. Okay. Sometimes the data set does not have column names. In this case, you need to specifically tell the function that there is no column name. Column names equals false. Then it will start to read. Sorry. It will start to read data from the first row. And automatically it will add column names for you. It will create column names for you. Of course, it will give you this kind of generic names like X1, X2, etc. And later on, you can rename them. So you can rename them later, or you can give a name at the beginning. Right? So you can create column name for yourself when you read in the data set. So this is read underscore CSV, this file, this function. We can also use this function to create a CSV file. So this is very interesting if you wanted to create a toy data set by yourself. So this is a very simple, the basic syntax. Just quote everything together. The first row will be assumed to be the column names, A, B, C, and starting from the second row, you specify the values for each column. The result is like this. Delimiter is comma because we use comma to separate them, and the column names are A, B, C, and the values are just assumed. Okay, so if you type numeric values, it will be assumed to be real numbers. All right. So notice that we also have some parallel functions in base R. For example, we have seen read.csv. So this is also available for us. Why do we have to use a read-R function? So that's because read-R functions are more efficient. So they are typically much faster, about 10 times faster than base equivalents, right? And they produce tables automatically, uh, and they are more reproducible. So these are the advantages of using read-R functions. And also they have more options like read TSV, read CSV2, etc. Okay, it allows different delimiters. And then the last page, the last slide shows you the connection between Dplyr and SQL for two table verbs. So for example, inner join, the inner join function in Dplyr. In SQL, we can do this: select asterisk from X, join Y on X dot A equals Y dot A. So suppose the key variable is A. So all of these joins have corresponding SQL code. So basically, the Dplyr package is trying to imitate SQL syntax and the way that SQL does query. So all of them are, if you are familiar with SQL, you know that these are the four types of joins. So summing, join, intersection, all of these are available in SQL as well. So consequently, Dplyr functions are also very efficient and very effective in dealing with data frames. All right. That's all for dealing with two tables. We talked about three families of functions: mutating joins, filtering joins, and set operations. So they all have their different functionality. All right, we still have about 15 minutes. So let's move on and talk about tidyr, how to tidy data. Because this is a summer class, we have fewer lectures, fewer class time classes than regular semesters. So I have to, teach faster, a bit faster. All right, so I will just use the Wrangling webinar, this set of slides. So we'll start from slides 13 and talk all the way to slides about 77. So this part is for tidying data. And this set of slides also contains a summary for Wrangling 1 table, Wrangling 2 tables. It's a very good summary about everything about data wrangling. Of course, it provides some different examples, simpler examples actually. So you can read through all of the slides if you want to do a review. All right, let's start from here. Okay, so we will use this package, data set in this package, right? EDAWR. There are 4 data frames: storms, pollution, cases, and TB. So actually, we won't use the last one today. We will only use the first 3. And take a look at the 3 data frames. Storms, 4 columns. The storm name, wind speed, pressure, air pressure, and date. Okay, so it's a very simple data set. It's sort of in a tidy format already. The second one is cases. It's called cases. So apparently this is a contingency table. It contains some summary data. If we decompose the information into three parts, it contains country information, and year information, and some counts in the table, right? And lastly, the pollution data set. It looks quite tidy. Um, it's it has 6 rows and 3 columns. Okay. Now let's decompose the information in a special way. City, um, amount of large particles, and amount of small particles. Right? And the reason that we summarized the data frame in this way is because we will try to rearrange or transform the data set into a different way. Okay. So let's see. We can actually create a new variable using existing variables. For example, we create a variable called ratio, which is equal to pressure divided by wind. So it is definitely possible. And then let's see what is the definition of tidy data. Very simple. Each variable is saved in its own column. And each observation is saved in its own row. And then each type of observation stored in a single table. Here is storm. So a table is very kind of specific. Right? It contains information about a specific type of information. So in this part, we will talk about this package, tidyr. Okay. This is also included in tidyverse. It has 4 functions. Let's talk about the first two. First group, gather and spread. So these 2 functions are used to reshape the layout of our table. If you want to take a look at the documentation of these 2 functions, you can load the package and then type !gather or !spread. So let's first take a look at this cases table again. It has 3 pieces of information: country, year, and count. Okay, but apparently this is not in a tidy format because each row contains 3 years of information of a country. So it's not that tidy. Suppose we want to create a new data frame with 3 variables: country, year, and count. Okay, so 3 of them separately. Not in this format anymore, with 3 columns: country, year, and count. Then what should we do? So first list the 3 columns: country, year, and count. Call it N. Then let's see how to convert the each cell to this to each row. Okay? So actually, just each cell in the table will become a row. Okay? Of course, together with the row name and column name. The first observation will be corresponding to France in year 2011 and the count. Similarly, the second country, third country, US in 2011, and then move on to the second column. So totally we have 9 cells. There are 9 cells in the table, so there will be 9 rows in the new table. So this is called gather. Why? Because we gather the information from the 3 columns, 2011, 2012, 2013, gather them together and put them in 2 columns, year and N. Okay. So in this case, notice that the column names 2011, 2012, 2013 are used to create a new key variable called year. Okay. So the column names become values in the key column. Okay. And the cells, the entries, become the third column, the values of the third column called N. Notice that both of these columns, year and name, did not exist in the original table. So we need to create them by ourselves. So the syntax for the previous example is this: gather, cases, this is the data frame name, right? Data frame we want to reshape. And then the new variable that contains the key values. So name of the new key column. The values of this one are the original column names. And then the new variable we created to contain the cells, right, the entries in the table. The new value column. So this is a key. This is the value column. Key value column. And lastly, the names or numeric indexes of columns to collapse. Oops. So 2, 2, 4. You see 2, 3, 4. In the cases data set, we collapsed the second, third, and fourth columns together and create these two columns. So this is how the gather function works. So this is a summary. The two new variables, you should put them in this order: key, new key column, new value column, and then a list of columns to collapse. And then let's move on to the second example, pollution. So the pollution data set contains information like the amount of large particles and small particles in 3 cities. Suppose we want to reshape this pollution data frame to a new data frame with 3 columns: city, large, and small. City, large and small are apparently new columns, but these two values, the column names, are originally values of the size column, right? So in this case, let's see how to reshape it. Imagine how we reshape it. 3 columns, and then the first row will become this part of the first observation, and the second row becomes the second number in the first observation for new row. So basically, we want to create one observation for each city, collapse it. So originally we have 2 rows for each city. So now we have 1 row for each city. In order to do this, we use spread. Why? Because we actually spread the table. Although this is a special case because originally we have 3 columns and now we still have 3 columns. That is only because there are only 2 levels in the size data set, in the size column. Imagine if there is 1 additional category, which is median, okay? Then naturally we will have 1 more column, which is large, medium, small. So totally it will become a data frame with 4 columns. So you essentially spread the original column to a wider one, original data set to a wider one. So that's why it's called spread. It really depends on how many levels are contained in the key variable. So let's see. So the column that we use to create the new column names is called the key column or key variable. So we see we use the levels or values of this variable to create column names, to create new values, new variables. And then the column that contains the cell entries are called the value column. So notice that in this case, both of the two variables exist in the original data set. So this is syntax: spread the data frame pollution, and then specify the key column, namely the column that we use the values to create new variables. Okay. In the original, in the pollution data set, size is the key column. Okay. And similarly, we specify the value column, which contains the cell entries. So in the pollution data set, amount is the value column. So notice that in this case, you don't need to use quote anymore because they both exist in the pollution data set already. So this is how it works. The value of size becomes column names. The values of amount become cell entries. So this spread. And apparently, spread and gather work in exactly the opposite ways, right? Spread will make a table wider theoretically, and gather will make a table narrower theoretically. All right. The last two functions in tidyr we will talk about are the unite and separate functions. So these are used to combine columns together or separate columns, split columns. For example, in the storms data set, the last column, date, contains three pieces of information: the year, month, and day. Suppose we want to create a column for each piece. Namely, we'll create three new variables, year, month, and day. We can do the following. Right? Separate, specify the data frame, storms, and then the variable we want to separate. And then a vector of new column names, namely year, month, and day. Use quote. And then lastly, specify the separator that were used in the original values. The separator was hyphen, so we use quote hyphen. And then the separate function knows how to separate the values. Right? So the hyphen is served as a separate delimiter. Right? And then we get this. And notice that in storms 2, the date variable is gone. It is replaced by these three columns. So this is separate. So very intuitive. So it will not change the number of rows. It will only change the number of columns. Unite works in the opposite direction. For example, let's take storms. And then we want to create a new variable called date, which is a combination of the three variables, year, month, and day. So basically, you first specify the new variable, and a list of variables you want to unite together. And then lastly, specify the separator. If we want to transform it exactly back to the storms data set, we can use the same separator hyphen. And then this is the result. I will create a new variable called date, which unites the three pieces of information together. So now in the storms data set, you see year, month, and day are gone, and only date exists in the result. So this is the unite function. You have the option, you can change the separator. For example, you can change it to slash or period or space. All of them will work. So it's quite flexible. All right, I think, yeah, so this is a summary of the four functions. So gather will make observations from variables. Spread will make variables from observations of one column, and split and merge columns with unite and separate. All right, we're done. Great. Next time we'll talk about how to impute missing values using R packages, which is